Before we can discuss solid surfaces, we have to have a quick review of solids themselves. We're going to be looking only at crystalline solids, and to simplify things, crystalline solids with cubic structures. And we're only going to look at 3 cubic structures. So we'll start with simple cubic. So with any crystalline structure, we can represent it as a lattice. And within that lattice, we can identify a repeat unit, which is sort of the simplest repeating unit within the lattice. We call this the unit cell. So first we'll look at the simplest type of cubic structure, simple cubic. All the images of the different types of cells are taken from the OpenStax chemistry book, which is free, and you can download it from the website of OpenStax. Okay, so here we have the lattice points. They're all on the point of a cube, and so we can see what it looks like if we put atoms on those points in the lattice in simple cubic. If we do space filling, that's shown down here. And one thing to remember is that if we wanted to know, for instance, how many atoms are inside a cell, inside the unit cell, we might be tempted to say 8. What we have to remember is that these atoms, since they're on corners, are shared with 8 other cells. So we can see there's cells above and to the side and in front and back. And so really, we have only 1/8 of an atom on each of these points. And that means that there's 8 corners, 1/8 of an atom each. So there's actually only really 1 atom worth of atoms inside that cell. The second thing to point out is the coordination number. That's just the number of nearest neighbors that each atom has. And so if we look at this, we can see that in a simple cubic lattice, you have a neighbor above and below and front and in back and on left side, right side. So we have a coordination number of 6. As simple cubic, we can just abbreviate as SC. Next structure we'll look at is body-centered cubic. So we can see that we have the lattice. This is just like simple cubic, but inside the lattice we put another atom in. So this is abbreviated BCC. And if we look at the coordination number for this, we can see that each of these center atoms, these are body atoms, has 8 neighbors. And similarly, if we were to look at one of the corner atoms, we could see that they're touching an atom inside this cell, but they're also touching an atom in the 7 adjacent cells, so their coordination number is also 8. Finally, we have face-centered cubic. In this case, there's not an atom inside the center of the box, but instead we put one on all the faces. And the coordination number here is actually equal to 12. So this is a much closer packed array of spheres. And because atoms are attracted to one another, closer packed is more favorable. And so we see a lot of elements, a lot of metallic elements have an FCC crystal structure. Some have BCC. SC, with its low packing efficiency, is actually very uncommon. The only element I can think of that has that as its packing structure is polonium. An important thing to note in all these structures are which atoms are touching. So in this diagram, the corner atoms and the face atoms are touching, but the corner atoms are not touching each other. We go to BCC, all the gray atoms are touching that center red atoms, but they're not touching each other. Whereas if we went back to simple cubic, we actually are touching along the edges. So you have to be aware of that when you're working with all of these structures, because it's going to play a role in the geometry when we figure out the surface energy of these materials.